Hi everyone. So in the last lecture, we studied Z transform and we looked at the definition of Z transform and we computed Z transform of some finite duration sequences. Now today we will move further and we will see how we can compute Z transforms of infinite duration sequences. So just to revise, in previous class on Z transform we saw Z transform of a sequence xn is denoted by x of z and it is defined as summation over n where n is running from minus infinity to plus infinity x of n z to the power minus n, and this z is a complex variable. So we can say, let's say this z is equal to real part of z plus j times imaginary part of z. This is in the rectangular form, and in the polar form you can write it r e to the power j omega. So this is the definition of z transform. Now before moving on, I would like to explain that what is the range of r and omega. What is this r and what is this omega? If I ask if r equals 1, then this r equals to 1 represent what in z plane? This z is complex. So let me draw this complex plane. Here this x-axis is real part of z and this vertical axis is imaginary part of z. So this is called z plane. And if I ask what would be the contour r equals to 1, so this r equals 1, this would be a circle in z plane. This is the circle in z plane. So this is the circle in z plane whose center is origin. 0, 0 is the center of this circle and the radius of the circle is r equals 1. So r equals 1 represents a circle of unit radius with center being origin in the z plane. So what is the range of this r? Because this r is nothing but the radius of the circle. Therefore naturally r has to be positive and it can take any value between 0 and infinity. So r lies between 0 and infinity. Similarly, what about omega? Omega is the angle and this angle can vary from 0 to 2 pi, or in other words it varies from pi to minus pi. So I can say omega lies between 0 to 2 pi. This is the range of r and omega, and this is the z plane, and r equals 1 represents a unit of radius, a circle of unit radius with center being origin in the z plane. Now we will see how we can how we can define the ROC of xz in terms of r, where r is what? R is the mod of z. This z is what? R e to the power j omega. And in previous lecture, we saw that what is the ROC of exit? The ROC of exit can be defined as the set of values of z for which series exit converges. So the range of values of z for which series exit converges, that range of z is called region of convergence or ROC. Now because this z is r e to the power j omega and r is equals to mod z, so it's very obvious that ROC is nothing but the values of r or the values of mod z for which the series exit converges. Now omega being angle, it will not affect the ROC. So from the definition of ROC, what we can conclude? This exit is xn summation xn z to the power minus n. And the ROC means what? Where the mod of exit is finite. Now why I am saying mod of exit is finite? Because exit is not necessarily a real function of z. Exit is what? It is a complex function of z. Therefore, we can find the ROC by finding the range of mod z where mod of exit is what? Finite. So when this mod of exit would be finite. So this mod of exit would be equal to summation mod of the summation xn, and now I can write z equals what? Z is r e to the power j omega. So I can write it r to the power minus n e to the power minus j omega n. So mod of this. So this summation, the mod of this summation should be finite. Now we know that from the triangle inequality, mod of a plus b would be less than or equal to mod of a plus mod of b, where a and b are two complex numbers. And therefore what we can conclude from this triangle inequality, this mod of summation x of n r e to the power j omega minus n, this would be less than or equal to summation. Now this mod is going inside, mod of xn r e to the power j omega minus n. Now you know from your knowledge of complex number, if there are two complex numbers z1 and z2, and if you find their mod, what it would be, let's say z1 is r1 e to the power j theta 1 and z2 equals r2 e to the power j theta 2. Now if you multiply z1 and z2, you get r1 into r2 e to the power j theta 1 plus theta 2. So if I take the mod of product of complex numbers, what it would be? It would be r1 into r2. So if you try to find out mod of product of two complex number, it would be simply product of their respective mods. Similarly, if I ask angle or the argument, so this is the angle or argument. Sometimes it is written as arg z1 z2, or it can be written this angle sign Z1 Z2. So what is the angle? So the angle of the product is what? Here you can say, here you can see it is what? Theta 1 plus theta 2. So when you multiply two complex numbers, what happens to their mod? Their mods get multiplied, and what happens to their angle? Their angle gets added. Okay. So now there are two complex functions xn and r e to the power g omega. So what will be the mod of, if I take the mod of this, you can assume it is like z1 and it is like z2. So this would be less than or equal to summation mod of xn. And what will be the mod of this? Mod of this r e to the power j omega is what? R. So you can write it is what? R to the power minus n. Now r being positive, you can write it mod of r is r, therefore it is r to the power minus n. So this summation, which summation? This mod of xz is less than or equal to summation mod xn r to the power minus n. So what we conclude from this discussion? We conclude that mod xz is less than or equal to summation mod xn r to the power minus n, where n is running from minus infinity to plus infinity. So this mod xz will be finite if this thing is finite. So what is the condition for the existence of Z transform? That this mod xz would be, mod xz should be finite. And when mod xz should be finite, if this thing is finite, because mod xz is definitely less than this. If this quantity is less than C, then this quantity is also less than C. So if this quantity is finite, then this quantity is also finite. So what is the condition for the existence? That for existence of Z transform, this summation should be finite. Which summation should be finite? Mod xn r to the power minus n. This should be finite. Or I can say the sequence xn r to the power minus n should be absolutely summable. You can write this summation also like this. You can take this r inside the mod. So xn r to the power minus n mod. This thing should be less than infinity. These two are same. There is no difference, r being positive. So when Z transform will exist, if sequence xn r to the power minus n is what? If it is absolutely summable. Absolutely summable means first you take the absolute value of what? Xn r to the power minus n, and then sum it up, and this summation should be finite. If this summation happens to be finite, then we say the sequence xn r to the power minus n is absolutely summable. Now again, there is one more interesting point. Now this summation depends upon r and x as well. So this summation depends on two things: given sequence xn and the value of r. Now for the given xn, the summation, which summation? This mod xn r to the power minus n may be finite or it may be infinite. it depends on R or infinite. Now, for those values of R for which this summation becomes finite, those values of R or that range of R for which this summation is finite, that range is called ROC. So now we are ready to give the new definition of ROC. So what is ROC? ROC is the range of values of R for which this summation mod xn r to the power minus n is finite. So now we are having the new definition of ROC. So region of convergence can be defined as the range of values of R for which mod xn r to the power minus n is finite, or for which the series xz is convergent. So if somebody asks us to find ROC, means what we have to find? We have to find the range of R for which this summation mod xn r to the power minus n is finite. Now we shall take some examples. In previous lecture on introduction to Z transform, we took some finite duration sequences and we obtained their Z transform. Now let's say we have a sequence which is called Kronecker impulse, denoted by delta n. The impulse in discrete domain is called Kronecker impulse, whereas the impulse in continuous time domain, represented by delta t, it is called delta Dirac function. So there is a difference between delta t and delta n. I am not going to define delta t. I am simply defining first how this Kronecker impulse is defined. This is defined as 1 for n equals 0 and it is 0 for n not equals 0. So if you draw this Kronecker impulse, it would be looking like this. This would be having value of 1 at n equals 0. This is our n axis and it is 0 elsewhere. So this is also called unit impulse. Precisely we should call it unit impulse. And in general, how we can define this Kronecker impulse in general means its shifted version. Delta n minus n naught. This is defined as 1. Now, what is here in the argument? N minus n naught. So, this would be 1 when argument is 0. That is when n is n naught. And it is 0 when the argument n minus n naught is not equal to 0. Which means when n is not equal to n naught. So, if you draw this shifted version of impulse, how it will look like? It looks like this. Here it is again 1. Its strength is 1. Its amplitude is 1. But not n equals 0. This point is what? N naught. And elsewhere this these values are what? 0. So this is delta n minus n naught. This is how we define impulse, and you can see it is unit sample sequence. It has only one non-zero samples. Rest of the samples of this sequence is rest of the samples of this sequence are 0. Now, our interest is to find the Z transform of unit impulse sequence delta n. Naturally, this is also a finite duration sequence. So, what is Z transform of this? Let it be xz. And from the definition, it is what? Xz would be what? Summation over n xn z to the power minus n. Now this summation would be 0. So it would be non-zero only for n equals 0, because the definition of delta n says what? It is 1 at n equals 0, and it is 0 if n is not equal to 0. So what this summation would be? Only for n equals 0, it would be non-zero. So if you expand this, you get x of 0, z to the power 0, and x of 0 is 1, z to the power 0 is 1, so it is 1. So z transform of Kronecker impulse or unit impulse is what? 1. Now if I ask what is the ROC, so one will remain 1 forever. It doesn't depend on R. So the answer is ROC is entire Z plane. For all values of Z, this xz is 1. So this is the only sequence for which ROC is entire Z plane. We saw that for finite duration sequence, ROC would be entire Z plane, but there would be exclusion of two possible points. One is R equals 0 and another is R tending to infinity. So here we close the discussion on the Z transform of finite duration sequence, and now we move towards the discussion on Z transform of infinite duration sequences. So consider this sequence: xn equals half to the power n un. Now before defining this sequence, let me define un. Un is called unit step sequence, denoted by unit step sequence is denoted by un. And how it is defined? It is defined as 1 for n equals or greater than 0, and it is 0 for n less than 0. So if you try to draw this sequence will be having non-zero samples for n equals 0 and greater than 0. So it is 1 at 0, it is 1 at 1 also, it is 1 at 2 also, and so on. In positive side, it is 1 for all the values. Whereas in the negative side, all values of un are what? 0. So this is how we define what? Unit step sequence. Why I am calling it unit? Because its amplitude is 1. And in general, I can define step sequence as follows. Let's say it is 2 times u n minus 3. How you will define this? This sequence would be 2. Now what is inside the argument? N minus 3. So I will write it is 2 for n minus 3 greater or equal to 0, which implies for n greater or equals 3, and it is 0 for n minus 3 is strictly less than 0, which implies n less than 3. So if you draw this sequence, how it will be represented in pictorial form? Now this sequence has values what? 2 for 3 onwards. So it is 2 at 3, it is 2 at 4, it is 2 at 5, and so on. So it is 2 till infinity. But in for the values of n less than 3, what would be the values? 0. So at 2, what is the value of this? 0. What is the value of this at 1? It is 0. What is the value of it at 0? 0. What is the value at minus 1? 0. So for n less than 3, the values are 0. This is called unit step sequence. Now this half to the power n un, this sequence is in fact exponentially decaying sequence. Half to the power n is what? Exponentially decaying sequence. Now before drawing half to the power n un, can I draw half to the power n? So first I draw half to the power n. So this is our n axis. Now half to the power n, it is at n equals half to the power n. Now I will take values of n what? 0, 1, all integers. So at n equals 0, what is our value? Value of the sequence is what? 1. Where? At n equals 0. Because half to the power 0 is 1. If I put n equals 1, what value I shall get? I shall get half. So here I can write it is half to the power 0, which is in fact 1. Then what value I will get at 2? I will get half square, that is 1 by 4, and then half cube, that is 1 by 8, and so on. This is in positive side. So values are decaying in positive side. So it is not in fact exponentially decaying. See, it's an exponentially sequence. Now what is value at minus 1? You will put n equals minus 1. So at n equals minus 1, its value will be what? 2. At minus 1, what will be it what would be its value at n equals minus 2? It will be 2 squared, and so on. So in positives, you can see in negative side it is growing. So but as your n increases, its value decreases. Okay, so its value of half to the, it's an exponential sequence, and its value varies from infinity to 0. For n equals minus infinity, its value would be infinite, and for n equals infinity, its value would be what? It would be 0. Now this sequence is multiplied by un, because what you are given, you have to find z transform of not half to the power n. You are asked to find z transform of half to the power n un. So I draw un. This is my n. So un means what? It is 1 for n greater and equal to 0. So this is my un, and here in the negative side it would be 0. So at minus 1 it is 0, at minus 2 it is 0, and till minus infinity it is 0, but 0 onwards it is what? 1. Now this green sequence is u to the power n, and red sequence is half to the power n. Now if you want to multiply two sequences, you have to multiply them sample by sample. Sample by sample means the value at 0 of this sequence would be multiplied by value at 0 of this sequence. Value at 1 would be multiplied by value at 1 of this sequence. Value at 2 of this sequence would be multiplied by value at 2 of this sequence, and so on. For un, the values are either 1 or 0. And you know, 1 multiply anything remains the same thing. And whenever you multiply 0, that number becomes 0. So when you multiply half to the power n with un in negative side, it would become 0. Because at minus 1 it is 0. So 0 into 2 would be 0. 4 into 0 would be 0, and so on. So in negative side, this multiplication will result in 0 values. Whereas in the positive side, what you will get? 1 into this, any number would be the same number. So there won't be any change in the positive side. So what is half to the power nun? Now I draw half to the power nun. This pink sequence is multiplication of this two sequence. Which two sequence? Half to the power n and un. So as we have seen in negative side, this product would be what? 0. So at minus 1 it is 0, at minus 2 it is 0, at minus 3 it is 0. But what about this product in the positive side? At n equals 0 you would be having what? At n equals 0 value would be 1. At n equals 1 value would be what? 1 into half will be half. At value at n equal to 2, what it would be? Half squared into 1, that is half squared, that is 1 by 4, and 1 by 8, and so on, and exponentially it will become 0. So this is now an exponentially decaying sequence. So but one-sided exponentially decaying sequence. In negative side, the sequence is 0, and in positive side, as n is growing, the values of this sequence are becoming lesser and lesser. So this is an exponentially decaying sequence. Exponentially decaying sequence. And our job is what? Our job is to find its Z transform. So now again we shall use the definition and we shall try to find out its Z transform. So half to the power n, can it be expressed in two pieces? Half to the power n. What I can write half to the power n from the graph? From this graph, it is very much clear that it is half to the power n in the positive side and 0 into negative side. So what I can write, half to the power n un is in fact half to the power n for n greater and equals 0, and it is 0 for n less than 0. So this kind of representation of sequence or signal is called piecewise representation. Why piecewise representation? Because this closed expression half to the power n, now this has been split into two pieces. First piece is half to the power n for n greater or equals 0, and other piece is what? It is 0 for n less than 0. So this we call what? Piecewise representation. What we call it? Piecewise representation. And now we have to find Z transform. So from the definition, this xz is what? Summation over n. N is running from minus infinity to plus infinity. Xn, z to the power minus n. But from this piecewise representation, it is very much clear that sequence is 0 for n is strictly less than 0. So this summation would become 0 if you split this summation into two parts. One part from minus infinity to what? 0? No, it is from minus infinity to minus 1, and other part is from where to where? It is from 0 to infinity. So my sequence is 0 from where to where? From minus infinity to 1. So this summation would vanish. You will get 0. And then the remaining summation, I can write what is inside that remaining summation. Xn is what? Half to the power n and z to the power minus n. Now, if I write the summation like this in n running from 0 to infinity, half z inverse to the power n. Yes or no? Can I write like this? And now if I expand this summation, what shall I get? I shall get, I will put n equals 0, 1, 2 and so on. So half z inverse to the power 0, that will give me 1. Then I will put n1. It gives me half z inverse, then half z inverse squared plus half z inverse cubed and so on. There are infinite terms. So can you observe something? Is it a special kind of series which you have studied in your school? Can you see some pattern in this series? Yes, it is a geometrical progression. It is a GP. So the series of this form A0 plus A0R plus A0R squared or A0R cubed and so on. There could be n terms or there could be infinite terms. So let's say this is a series, summation of these numbers, and it is forming a geometric progression. And if you assume there are infinite terms, so if I represent this summation by S, can you guess what this S would be? This S may be finite or this S may be infinite. So this series may be converging or it may be diverging. Depends on what? Depends on the value of what? R. So this summation is A0 upon 1 minus R. This A0 is the first term of GP and R is what? Common ratio. If you divide two successive terms, let's say second term by the first term, you get R, or third term by second term, you get R. So R is common ratio. But this summation is finite provided if this mod of R is what? If it is strictly less than 1. Now, if it is not, if this condition is not satisfied, then the summation of this infinite GP would be diverging. It would be infinite. So, here you are seeing what is our exit. Exit is 1 plus half Z inverse to the power 1 plus half Z inverse squared. So, it's a infinite GP. It's an infinite GP. So what would be this summation? What is our first term? It is 1. What is our common ratio? If you divide this third term by the second term, you get half Z inverse. So 1 minus half Z inverse. But this summation is possible only if what? If half Z inverse mod is what? Is strictly less than 1. So what I can write, I can, if I simplify this, I shall mod of half will be half, and then I can write mod of Z, because it is Z inverse, I can write it 1 upon mod Z. It should be what? Less than 1. And if I take this side, so what I get? I shall write on next page. So what I get? I get xz is 1 upon 1 minus half Z inverse provided half 1 by mod Z is strictly less than 1, or this implies mod of Z is strictly greater than half. So this mod of Z, this is what? You know this Z is what? It's a complex variable R e to the power j omega. So what is mod of Z? Mod of Z means R. So R is what? Greater than half. And if you want to remove Z inverse and if you want to write the expression in terms of Z, what you can write, the same expression can be written as Z upon Z minus half provided mod of Z, which is R, is strictly greater than half. So this is the Z transform of half to the power n un. Now if you like to draw the ROC in Z plane, how you can draw? So I draw the ROC. ROC is what? Again, it is the range of R for which this exit is converging. So what is that range? That range is what? R is strictly greater than half. And we have already seen that R equals 1. It is what? It is a contour. Which contour? It is a circle in Z plane with unit radius, and what is its center? Its center is at origin. So what will be this contour, this region? R is strictly greater than half. So first I draw the z plane. This horizontal axis is real part of z. This vertical axis is imaginary part of z. Now I have to draw a region which is greater than half. So before that, if I ask what would be the region r equals half, r equals half would be circle in this z plane whose radius would be half and whose center would be what? Origin. So if I draw this, this is the circle with radius of not 1, with the radius of half, and its center is what? Origin. Now I have to draw the region which is greater than half. So greater than half means what? Exterior of this circle. So I draw the exterior of this circle with the green color. So this is the exterior outside this circle. So this green region which is outside this red circle, this would be our ROC. So if you are in the Z plane, in the green region, Z transform exists. But if you are inside this red circle, then Z transform will not exist. So with this, I stop here. In next lecture, we will take some more examples on Z transform. Thank you very much.